Okay, so I'm going to start out first just with a few words about the report that's due next week. If you're still working on it, some people are already finished. And there's no real new information here, but I might just kind of remind you about a couple of things. Sample calculations, you want to pick either the second or third column on the data sheet and show all the calculations you did for that. And of course, nice and orderly where someone else can look at it and follow what you're doing. Show the formula and show the numbers being plugged in and show the answer. Um, but the rest of it is just generally repeated, but with different values. So that's why we don't require you to show everything, but just pick one of those columns, either the second or the third, because, and just show all of that, and that's sufficient, okay? Don't do the first because there are some things you don't have to do for the first column that you do have to do for the second and third, so it wouldn't be complete then. Okay, so just show everything you did for either column 2 or column 3. Okay, then on discussion, I'm not going to tell you anything new that's not in the lab manual, but maybe I'll just maybe I can get it across a little more clearly. There's a couple of pages in the lab manual about a discussion about what we require on that. It's sort of overwritten, quite honestly. It's a little scary, maybe. But anyway, you might take a look at it, and I'll just remind you of a couple of things. What we don't really want you to do is you don't need to write some really long thing about all sorts of minute details about how you did the experiment. That would just be busy work. We don't really want you to do that, or at least, well, not for a weekly report anyway. So, you might just have start out with about 3 sentences or something about just generally what the experiment was about, what we were trying to prove in this experiment, and maybe just a little bit about equipment, but you don't need to go on too long about that. Okay, that's not really what we're wanting you to do. But then you want to say something about validation. We're more interested in having you analyze the results and talk about that than we are just rote procedure. So you want to say something about validation. That just means you're going to give your percent errors or percent differences, which I think in this one they were all percent differences. So that's not too bad. All you have to do is just say we got so much percent on this procedure and so much percent on that procedure, and there are 3 of them, so you can just list those. That's kind of a bottom line thing. Somebody reading your report, one of the first things they want to know is how close did you get to the right answers? How correct were you? So that's something you give there, all right? And generally you want percents to be good. I mean, if you're getting a really high percent, like bigger than 20 or 30 or something, then that means something's probably not right. So you want to try to figure out where you made a mistake. Okay. So then you want to talk about error sources, all right? You don't need to say, there's some things you probably shouldn't bother to talk about when it comes to error sources. There are some really obvious ones that you can assume are understood, like the fact that every time you do calculations, you might lose some significant figures and some round off error. And yeah, it's true, but that happens in any experiment you ever do in your life. So that's just sort of understood. So same way with the fact that every measuring instrument has an uncertainty. Yeah, it does. It's true. But you can assume everybody understands that already. Everybody knows that. You're not really telling them anything they don't know. Okay, so I wouldn't really bother to mention that. Now, if there's some particular instrument that has something unusual going on and you'd like to elaborate on why this instrument is not as certain as we would like it to be, that's fair game. You could do that. Okay, but error sources mainly you want to talk about things like the fact that the air track, it could have some sag or bend in it that we don't recognize. You can never get it exactly perfectly level. We say it's frictionless, but that's never really completely true. There's going to be some little bit of friction at least, some wind resistance, So things that you can't help and that are specific to this experiment. In other words, no matter how awesome a student you are, you can't help these things from happening. And they're specific to this experiment. They're not just the same old things that happen with any experiment. Okay, so that's the deal on that. And also, hopefully it's kind of obvious, but error sources also doesn't mean mistakes, like you goofed something up, you calculated something wrong. We're not talking about that. We're assuming you did everything correctly, okay? But it's unavoidable error sources, all right? Okay, I'll go on to the next experiment. Okay, so this week's experiment is one-dimensional collisions. And as you can see, it uses the air track again, like the energy experiment we did. But now you've got two gliders, in addition to the red one like we had before. Now you've also got this big blue one. And here's the kind of thing we're going to be doing. We're going to be looking at momentum, which is mass times velocity. And it's going to be conserved before and after the collision. So let's say we do a collision where we start out with the red glider sitting still, and we give the blue one a push, okay? Watch what happens. Okay, so what happened, let me do that kind of in slow motion. Like, okay, the red one sits still, we give the blue one a push, it goes to the photo gate, hits the red one, and then it's going to move as well, okay? So the original momentum that the blue glider had, it gets redistributed after the collision. Most of it goes to the red glider, but some of it is still left in the blue glider, okay? But the momentum would be the same before and after. The momentum that the blue glider has when it moves like this, okay? You can find out its initial momentum. Then after it hits the red one, then they're both moving, okay? And their momentums, or momenta is the correct word, added together after the collision should equal what the momentum of the blue one was before the collision. Okay, so that's the deal on that. Okay, so now let me say a little bit more about that. I've got the air turned off now, so maybe you can hear me better. Back to this collision, and a reminder what we're talking about, the big important quantity in this experiment is going to be momentum, which is mass times velocity. I don't know if everybody would have gotten to it in class yet by the time we're doing it, but you will soon, if not. The photo gates this time in this experiment can be moved, okay? In the energy experiment, they were fixed in one place, but in this one, they can be moved around, okay? So here I am scooting them around, all right? And you may find it necessary to move them sometimes. So you have to think about that in this experiment. Let's say if we weren't very careful about what we were doing and we did this experiment, okay? Let's say I tried to do it like, let's say I was going to try to do that same collision, and this is something that's a common mistake students make is let's say you start out with the red glider initially not moving, and you kind of put it between the middle of the gates. Well, if I give the blue one a push and it's moving, okay, then there's a problem. Hopefully you can tell in the video, but the glider is still in the gate while it's hitting the red one. Okay, the blue glider is still in the gate while it's hitting the red one. So I don't know how much of that flag has gotten through when the computer measures the time. Okay, what we need is for the entire flag to get through, and that way we know that the length of the flag, that entire distance, has gone through, and we can calculate velocity that way, and it'll be accurate. So that's got to happen. You've got to have a clean sweep through all the way through the gate. Not necessarily the glider, but the flag anyway has got to go all the way through the gate before it ever hits the red one, the red glider. Okay, so that way we know that it moved this distance in the amount of time the computer tells us, and we can find initial momentum pretty accurately then. if it was stuck in the gate while it hits, then, I have no idea what the momentum would be. Similarly, if I were to be careless and leave the red glider inside the gate while I did the collision, well, same problem there, okay? So anyway, the key thing is you need to have it arranged where the first glider that's moving can get all the way through and have a nice clean sweep through before it ever hits the other one, all right? Now, you might think, well, the farther apart I move the gates, the better then. Not necessarily, because if you move them too far apart, then what could happen is you go through the first gate, and then you go all this distance before you hit the red one. Well, that gives the blue glider more time to lose some of its initial momentum through wind resistance, and maybe the track isn't perfectly level and so on. So it's better to measure it pretty soon after it gets to the gate. Okay. So basically the lesson is you want them, you want the gates in a position, you want them arranged where, you get a nice clean sweep through, but not too far apart, not too much room. All right. So that's the deal on that. Okay. Okay, so here's just to show you a quick example of another kind of collision we'll do. What I showed you before was what we would call an elastic collision, where they bounce away from each other. Here we're going to do one that's called inelastic collision. And I don't know how well you'll be able to see this, but I put tape on these bumpers and the gliders, so there's tape around them. And it's wrapped around where the sticky side is out, okay? So we're going to do a collision where they stick together, okay? So what you saw there was initially, it was like before, the red one sitting still, the blue one gets the push. But then they stick together, and this time they're moving as one unit, and that changes things. Momentum's still conserved, okay? But that's another kind of collision we'll do in inelastic collision. Okay, so now let me say a little bit about how this experiment will go when you're doing it. Kind of similar to last week. You'll only be here 1 hour, and you come your specified hour. If you usually worked in room 103, then come the first hour. If you usually worked in room 105, come the second hour. In other words, the same way it was the last time we met, and you'll only be here 1 hour, okay? So you'll want to get the measurements and do as much calculating as you can while you've got us there to help you. And you can get that done in 1 hour at least, okay? But most of the calculating, you probably won't get it all done. You'll probably have to finish it up at home. An hour probably won't be long enough to do everything. Okay. And when you look at your data sheet, there's a lot of numbers to calculate, even more than last time, if that's possible. But you're going to calculate momentum for a bunch of different situations. And about 2/3 of the way down, you'll come to something called delta P over P total initial, okay? So that is like your percent error in this experiment. That quantity, the delta P over P total initial, would be 0 in an ideal world, all right? Because momentum's supposed to be conserved. In your case, unless you're just really lucky and really good, it'll probably be something other than 0, but hopefully not too big, okay? And we usually make an arbitrary cutoff of 15%. We'd like you to try to get less than 15% on those, okay? If you don't get it, then that means probably something ought to be redone, or maybe look at your calculations again, okay? We'll probably cut a little bit of slack this time because we're telling you can't be there the whole hour, but generally you want to shoot for 15% as a cutoff for your change in momentum, your fractional change in momentum. Okay, and it's going to be a report again like the last one was, and there'll be more details about that in the lab when you come here. All right. Okay, one more thing I'll talk about and then I'll stop talking finally. Um, okay, now next week we're going to do the one-dimensional collisions experiment like have been talking about. The week after that, the week of October 19th through 21st, we'll have a couple of tests for lab. Okay, a couple of exams for, well, an exam and a test. Okay, so let me say a little bit about that. There are two main things. We'll do a lab practical exam, which means you'll come in and actually do experimental sorts of things. And you have to do some measurements and some calculations that will be pretty much from earlier experiments we've done so far throughout the semester, or very much like them at least. Okay, probably pretty much the same things. Not an entire experiment, just some procedures from experiments. Okay, everybody will be doing something different. You won't all be doing the same thing, and whatever you get is just random when you walk in. Okay, so that's the lab exam. Also, you work alone on that. You do not work with a partner. All right, that could make a difference. So that's the lab exam. And then the second thing that we do is an assessment test for lecture. Remember the first week when we did the investigating emotion experiment, but you also had to do, there was also a test we took that was just a multiple choice test over general physics concepts. We'll be doing something like that again, another test like that. The idea is that by now, halfway through the semester, you've hopefully learned something about physics now that you didn't know before, and we want to test and see if you have. So that's the deal on that. It does not count for your grade. It's just something you have to do. Um, so, okay, so those two things, that'll be the week after next. All right. So I'll probably say more about it again following next week. So we'll know more about it then. All righty.